So for this problem, we have an airplane with thick aluminum walls on either side of the cabin, and we want to model using a resistance network the temperature difference, the heat loss of the cabin to the outside air. So as we can see, we have the initial, the convection on one side, the resistance of aluminum, and convection on the other side. So we can assume it's steady state, it's 1D, and we have the inner surface temperature of the aluminum wall. So we have 1D transfer, thermal conductivity is constant, heat transfer by radiation is negligible, and there's a flat wall on one side of the airplane. So the area is 2.6 meters, so we first find our convection 1, that's 1 over H1A, we use the first H1, that's the H1 from the left side, and you get this value. Then our R of aluminum, again you use K instead of H, and then same with our R naught, or our R of the outside. Then we add all of our R's together, and then we can find our total rate of heat transfer by taking your difference in temperatures over your R total. You get 394 watts. We can then find our Q dot by solving for we can find T1 by solving for T1 is equal to T infinity minus Q dot R convect 1. We get 4.85 degrees C. And then our 1D analysis shows that we have a heat transfer rate of 1,976 watts, which is way off, and shows that resistance means a lot when in conjunction with these problems. So this is just a general find a spherical shell volume element with one-dimensional transient heat conduction, and then we determine the 2D transient heat conduction equation and the boundary conditions necessary to solve that equation. So first we know K, theta, R, and phi. Then we find 1D transient heat conduction for a sphere and 2D transient heat conduction for a sphere. So we assume no generation, transient, constant thermal conductivity, one-dimensional, and infinitely thin sphere. So we can solve by assuming we have a small piece of shell, and we eventually get our limit as the change in time goes to 0 is equal to this. And then our heat transfer in the radial direction is equal to our conduction equation. Fourier's law, sorry. And then we have just continuing to solve, and eventually we get this equation here. Then for 1D, so this is 2D, so that's for 1D, this is for 2D. We add our thetas and phis, and we get that equation. So our boundary conditions are thermal symmetry because it's a sphere, so it is symmetrical about the sphere. At x equals 0, T1 is given, and then our other temperatures, and Q dot, our rate of heat transfer, is also given. So for this problem, we have a droplet that is released into the air, and we have the Q of system is equal to Q of radiation. It's assuming we have no heat loss, all of the heat loss is due to radiation, and our change in temperature is directly from that radiation. So we can use MCP delta T is equal to epsilon, or E sigma AS TS to the fourth, T surroundings to the fourth. And we're assuming it's stationary, we have a black body and a gray body, and it's a perfect vacuum, and the droplet of water is a perfect sphere. Our temperature surroundings was from University Science Guys, and that's what the temperature of space is. We have a given R, our initial temperature of water, and our heat capacity of water from table 14-7. So plugging that in, we get temperature final of 305 Kelvin.